Behold the unmoving tennis ball. As we can see, when I move the tennis ball, it comes to a stop. But what really causes the tennis ball to stop? This. The uneven surface of the table causes a grip on the tennis ball, which results in a loss of velocity as it continues to roll. Now, despite popular belief, when it's slowing down, that's actually acceleration in progress. Now, same thing. When I drop the ball, that's also acceleration in progress. A lot of people will have a misconception about this, but when it speeds up and slows down, that's actually acceleration in one direction. A lot of people may ask, like, how? How is it acceleration in one direction if it's going two directions? And, well, the answer to that is simply it's slowing down in one direction. So, essentially, you see it going here, but you see it slowing down. And then you see it come back, but faster. So what's happening there is that actually the acceleration is the net force on the object. But there is no net force on the object going in this direction. So essentially what we have is that initial amount of force interacting with the object. But that force does not stay because the force of gravity will pull it back down. So essentially what we have is this one direction of acceleration acting on the ball. It's always down. Now I get some people may still be confused, and they're even questioning my logic, like, where's the math? And for that, well, I've written the math. Now the first thing we need to understand is is that gravity exists. Number 2, gravity is constant. So for instance, here where your hand throws the ball, that initial force applied is there when it's up until the point that it leaves your hand. As we can see, there's still a finger there on the ball. And then you also have that constant force of gravity. Here we see the ball is on the rise, it's left your hand, so that force that you applied is no longer there. And the only force acting on the ball is gravity. Here we can see when the ball hits its highest point, also the only force acting on it is gravity. And then here we see when the ball drops, the only force on the ball is gravity. To better explain this, if the force of gravity was not constant, this pencil would be flying onto the ceiling. So here we can see the position time graph of the y-axis. So it started in your hand, it went up, and then came down. And then we can see here the velocity time graph. So it started out at that certain velocity and then slowed down here and then sped up essentially. So here we have this, so it slowed down, reached the origin, which is the vertex where it stopped, and then continued to speed up the opposite direction, which was the curve back down. Here we can see the acceleration time graph. As stated, gravity is constant, so you have it here because the acceleration time determines the slope of the velocity time. If the AT graph is a constant negative, then that means that the VT graph will have this constant downward slope. And then if we have this constant downward slope for the VT graph, that means that your XT graph will have this nice parabolic shape. Okay, so that's nice, but what if we changed things up? Let's say if we sped up and slowed down. Our graph would look something like this. Our graph would look something like this. Here I've labeled the directional changes in the acceleration graph on the XT graph. That would make our VT graph look something like this, where it would speed up here, and then it would slow down and then go downwards. So it would slow down until it reached that 0, and then it would go negative, and then it would go backwards. And then here where it would speed up again, but never get to that positive velocity, where it wouldn't go back up. And then that will bring us to our acceleration graph. No, ladies and gentlemen, you are not seeing triple. In fact, it just flips. So it would be positive, then negative, then positive. It wouldn't have a slope, because then this would be parabolic if it had a slope on the AT. You know what? I was kidding. It would actually be this. To imagine this hypothetical scenario in free body diagram, here we have the force of laziness being counteracted and completely overpowered by the force that I've applied with my feet. Now we see here that force normal and force gravity are canceled, so they don't have any effect. So we can see here that the force I apply is greater than the force of laziness, so I speed up. Now here, where I slow down, we can see that the force of laziness is greater than the force I've applied, meaning that the acceleration would be backward, or negative in this case. So clearly I would slow down because I become lazy, and when people are tired, they tend to slow down. Here's how to do the math. Your direction of your net force is the direction of the acceleration. And we know that net force equals the force applied minus the force of laziness. So we can then find this from the free body diagram to find the direction of the acceleration. Now let's talk about this. Here we have Earth and a table. The Earth wants the table to be like this. The table wants the table to be like this. So they compromise. The table stands its ground. But what happens when there's no ground to stand on? When the table has no ground to stand on, the Earth is completely in control. And that's when the only force on the table is force of gravity. Now you understand the gravity of the situation. Thank you for watching.